Hi everyone, my name is Soborno Bari from the Quran Institute, and today I'm going to show you my way of extending cosine and sine, and consequently all the other trigonometric functions, to the complex numbers. So how's this going to work? Well, it all banks on this. Now I know you've seen this identity before, whether you know how to prove it or not. Hint, it is based on the Taylor series. So, this is what we're going to use. Now, plug in what we know from this formula, which is how we define sine and cosine in the first place, right? With a unit circle in the Pythagorean theorem, this is sine, this is cosine. So, sine squared plus cosine squared has to be equal to the hypotenuse squared, which is 1. So, that means that cosine theta is equal to the square root of 1 minus sine squared theta. Now, e to the I theta is then equal to the square root of 1 minus sine squared theta plus I sine theta. So what I'm going to take advantage of is this minus sine squared theta is just I sine theta squared. So we redefine I sine theta is some new variable x, right? So then we get the square root of 1 minus x squared plus x. So now we subtract x from both sides to get this. And now we're going to plug in theta equals I. This means that x now has the value I sine I. Great. So then that means that we get, when squaring both sides, 1 minus x squared is equal to x squared minus 2 e to the I theta x plus e to the 2I theta. So now, this is going to be a little harder than I thought because this expands into a full quadratic. But no matter, we have now plugged in I for theta, which makes this minus 1 and minus 2 respectively, which means we can plug it into the calculator to get 2 times e to the minus 1 is 0.736, and e to the minus 2 is 0.135, so we get 1 equals 2x squared minus 0.736x plus 0.135, or in other words, 2x squared minus 0.736x, 1 minus this, minus 0.865, which looks eerily similar to cosine 60. But I think we can ignore it. Not cosine 60, cosine 30. Right. Okay. So, this is equal to 0, and now we can pretty easily find the roots if you want to, but it doesn't really matter. Well, first of all, we gotta actually see if it has real roots. So we have b squared minus 4ac, which is 0.736 squared, plus 4 times 0.865 times 2, which is obviously real. 0.736 squared plus 4 times 0.865 times 2 is about 7.462. So then, square rooting that means our discriminant, or the square root of our discriminant, is 2.732, and then we have 0.736 outside, and this is divided by 4, meaning we have two possible values. So we have either 0.8669, or we have minus 0.499. So I think we can estimate this one to be positive cosine 60, 30, and this one as negative cosine 60, which is kind of weird, but that's alright. And in fact, I'm pretty sure there's a real place where we can put this into action. You see, this is root 3 over 2, and this is minus 1/2. So, that means this represents a real place on the unit circle. Pretty sure, anyway. And that real place, that real place is either where, so this is, oh, wait a second. So this is x, which is I sine I. Which means sine I is actually root 3 over 2i, or better represented as minus root 3 over 2 times I. So, that is how we can represent sine I, and then cosine I, respectively, would then be b over 4. It could be 1/2, if I'm not wrong. Yeah, I'm pretty sure it can just be 1/2. I may be wrong. No, I'm definitely wrong. Wait a second. So you get minus 3 over 4 here. Wow, this is actually pretty interesting. But then for cosine, that means cosine squared has to be 7 over 4. That's definitely a little sketchy. So cosine could be root 7 over 4, or we could have sine be 1 over 2i, which would make this minus 1/4, and have cosine I be root 5 over 4. Whatever it is, it still smoothly converts or extends sine and cosine into the complex numbers. So that's it, and you can use the addition formulae for sine and cosine if you want further info. So that's it. Thank you everyone for watching, and we'll see you in the next one.